And to folks who are joining us online, it's nice to be gathered for this conversation. This is the last in our series of Fear Not, Facing Difficult Topics Faithfully, and we're closing out strong. We're delighted to have Jared Milson from Rhodes College with us today. He's a professor of philosophy, and honestly, the first paragraph of his bio doesn't make a lot of sense to me. So I'm going to read you the second paragraph, which says that in addition to all of these courses in his areas of specialization, he teaches courses on topics such as the philosophy of conspiracy theories, the philosophical and linguistic study of slurs, and also looks at practices of non-Western societies and the relationship between philosophy and science fiction, and the nature of artificial intelligence, which is why he's here with us today to offer, as he said, a brief guide for the perplexed. When we're done talking about all of these heady concepts, I hope we'll learn maybe a little bit more about vintage bike habits. So it's already a biking conversation. Already a biking conversation started aside passion here. So we're honored that you're here with us, and especially grateful for your time this morning. So thanks.
Hello, everyone. So, as Catherine introduced me, I'm Jared Milson. I'm in the philosophy department. I also teach in neuroscience, which is an interdisciplinary program. Brings together disciplines from psychology and biology together, and so I work in there as well. A little bit of background about me. I'm actually trained in the history of philosophy. That's how I did my PhD at Emory University. But it was toward the tail end of my PhD that I gravitated toward fields in mathematics, logic, computer science, and finally artificial intelligence. So now I teach a course on artificial intelligence for non-programmers. It was developed in collaboration with folks at Agnes Scott, which is my former institution, and Google, who brought some data science courses to Agnes Scott. We created a minor in artificial intelligence, and the course I teach now at Rhodes was the cornerstone piece in that. So it's an introduction to AI for non-computer science majors. So.
That would be this room.
Right, so I thought maybe I'm going to do my best. I am sure that I will still not have hit the right level here, but I will do my best. We'll see, I may have put too much content on here, which is obviously an occupational hazard, so we'll see, maybe I'll have to move through some things a little faster, because I want to make sure we have plenty of time for questions. So yeah, trying to give you a brief guide for the perplexed. I mean, the first thing we got to know is, what is AI, well, artificial intelligence? And as far as I can tell, there are at least 3 senses to this term, or at least as it's used popularly. The first is that it's an interdisciplinary research field that studies artificial systems capable of performing tasks typically thought to require human-level intelligence. So the idea is, these are things that, when you go out in the world, you don't find things other than humans really being able to do these tasks. Things like playing chess, or planning a trip, or figuring out how to get to your coffee shop. These are tasks that typically require some intelligence, and this is an interdisciplinary research field. So it brings together research areas from psychology, linguistics, philosophy, mathematics, computer science, just all kinds of things, right? So this field's been around for about 70 years, so we'll talk about that when I get to some history. The other thing CAMEAN is an engineering program. So this is where the things that get studied in the first area are being built by an engineering program. So it's aiming to build machines that have human-level intelligence, or even greater, especially in specialized tasks. For example, the AlphaGo system that can now play chess and the game Go, and all these different systems that can beat almost every human out there. So you might argue it's got higher than human-level intelligence when it comes to chess, or when it comes to the game Go. In any case, that's the engineering program. And then the last thing we'll hear usually AI referred to is the products or processes that get developed by one of these 2 fields. So now you hear a lot of things about generative AI, or all these terms like that, and you hear industry speaking a lot in terms of AI, and typically that's what they're referring to, are actually the products and the processes developed in those 2. So I want to give you just a really brief history. One important thing to remember is the history of artificial intelligence is just inextricably bound up with the history of computing and computer science. The 2 are really born together. So while AI may sound like this new thing, it's actually not that new from the perspective of computer science, because it's essentially hardwired into the very program of computer science, which emerged as a discipline not until the 1950s. So you see, actually, as early as 43, folks were building what were called artificial neurons using some models from biology and studies of the brain. They were building artificial neurons. By this, I mean not actual physical systems. These were theoretical objects. That is, they were essentially mathematical entities that would behave in a way that was analogous to neurons in the human brain. That was happening as early as the 40s. In 1950, a name you may have heard of, Alan Turing, kind of the so-called father of computer science, develops or introduces what he calls the Turing test. Well, he didn't call it the Turing test, but we now call it the Turing test. And that was a way to test whether or not a system had human-level intelligence. And his way, rather than trying to define intelligence in like a dictionary definition, he gave what was called an operational definition. He said, here's how you measure it. And the way you measure it is, if you can engage in a conversation with a system and you can't tell whether it's human or not, it's passed this test, and it qualifies as being intelligent. And that has historically been the kind of litmus test for intelligence. Now there's competitions, systems are getting better and better at this, but so that was an important milestone. The first neural networks built in the 1950s, we're going to talk about that briefly. John McCarthy, kind of the father of AI, he's trained in logic and some philosophy actually as well. He organizes this 2-month workshop in Dartmouth in 1956, and that's where the term artificial intelligence is coined. Now, it's important, I think, when we look at the history, and from the perspective of where we are at now, to recognize that the history of AI has been shaped by booms and busts. In the 50s and into the 60s, you have this era of optimism where systems are being able to do lots of things we just never thought machines could do, including play chess, and checkers was actually the first one. Chess was far harder than checkers. ELIZA, which was a kind of program that you could ask questions and it would act as a therapist. This was developed in the 50s as well. You can still see there's a version of ELIZA online now. But then in the late 60s and throughout most of the 70s, you have the first AI winter, which was where the expectations of AI burst, and it was realized that the problems that researchers were confronting were much harder than the ones they had already solved. In the 80s, you have this return of those neural nets developed in the 40s. Those fell out of favor very quickly because it was realized they had limitations. They couldn't do a lot of things that the non-neural net kind of systems could do, and so it was thought this is a dead end. But in the 80s, research picked up, and we were able to kind of get through the bottleneck in research and develop these systems. During the 80s, you have this rise of Lisp systems. Lisp was an artificial intelligence language. You have the rise of what are called expert systems. We'll talk about those real briefly. These are systems where experts in a field were consulted, and those computer scientists would formalize these as rules and then program a machine. So for example, medical diagnosis. Imagine consulting hundreds of doctors to find out, okay, if I've got this cluster of symptoms, what is likely to be the cause? And then they would formalize that and write a program. This was happening in the 80s and was picking up steam, and then in 87, probably along with the savings and loans crisis, but we got the second AI winter, where again, the optimism fades because the new set of problems proves to be much harder than what the problems that were previously handled. Throughout the 90s and 2000s, we have, of course, the rise of the internet, and this kind of jumpstarts a lot of AI research. From 2000 to now, we have the era of big data, right? That has revolutionized artificial intelligence. By big data, I mean the fact that we all carry around these kind of things all the time, collecting tons of data, and we're constantly engaged in systems that collect information about us. That has unlocked the potential of many new systems that were never going to be able to work previously because there simply wasn't enough data. And then, really since 2017, we have what we might call the deep learning revolution. This is where all the buzz is. Generative AI, this huge new explosion in systems that take a slightly different approach than those that had reached success previously. And so we'll talk about that. Okay, some important terms of concepts and terms. A lot of what I was talking about was what gets called classical AI, or sometimes it's called, I prefer the term GoFi. That's good old-fashioned AI. That's the word by John Ogden. GoFi. All right. So GoFi it's symbolic-based, it's logic-based. One of the main things that they do are they try to represent agents as planning. So imagine you've got an environment, the agent has a bunch of choices about what to do, and it has to think about the consequences of those actions and pick the one that optimizes whatever goal that they have. It's this kind of planning that led to search algorithms, and that's the heart of GoFi, search algorithms. So this is where you represent a problem as having a bunch of options with consequences, and then you search that space for an optimal solution. If you ever used Google Maps, which I know everybody does, you're using a search algorithm, okay? So this is a kind of classical approach to AI. Expert systems, like I was just discussing, is based on this program as well. Formalized, rule-based, easy to debug and find the problems. It's also very transparent. Like, programmers can get in there and see exactly what's going on. If the system made a wrong diagnosis in a medical case, if it's an expert system, it's pretty easy to figure out what happened and what went wrong, and to fix it. And the other thing is it requires much lower amounts of data. Now, Google Maps is not the greatest example, since that's a search algorithm that works on tons of data, but it doesn't need that. If you remember MapQuest, anybody remember MapQuest? MapQuest was a very low data intensive program, and it was a classic search algorithm. And then we had that in the late 90s. The way to think about GoFi is, you have a program, which is a set of instructions, or an algorithm, just a set of instructions that will bring you to some definite result in some task. And you have some input. So for example, I was playing chess, right? If you remember the program, Deep Blue beat Kasparov in the great the chess wars, the AI chess wars. If you think about there, you've got a program that will tell you essentially what is the best move given a certain state of the chess game. An input might be, this is where we're at in the game. And then the output would be, okay, make this move. Or if you're using a search algorithm, right? You have a program like Google Maps, you say, this is where I am and this is where I want to go. And the output is the directions. That's the model of GoFi. Now there's another side to AI that you've probably heard a lot more about, machine learning. So these are self-writing programs. They come in three forms, generally: supervised, unsupervised, and reinforcement learning. Generally, supervised learning is where you have some kind of thing you want to label. Let's say we want to label, say, images of dogs versus cats. And we know which ones are dogs and cats. And so we train the system to pick up on the characteristics of a dog in an image, right, or a cat in an image, and we tell it whether it got it right. That's supervised learning, because you can think about it as like learning with somebody who's telling you whether you got it right or wrong. Unsupervised learning is not like that. It's kind of a free-for-all. You throw the system into a bunch of data, and it's going to pick out patterns. And it may not correlate with what you think it's going to correlate with, but it's going to glom onto things that allow it to predict the next whatever it may be. We'll talk about that when we get to generative AI. Reinforcement learning is kind of somewhere in between. This is where you have an agent that's trying to perform some task, and it's only getting very simple reinforcement. It's being told, you got that right, you got that wrong. So this is often the case in video games. We design agents that then play video games, and they get rewarded if they pass the level or beat the game. And if they don't, they get punished, so to speak. And what the system's trying to do is it's trying to figure out, okay, well, what do I have to do to pass the level? And so it might start off randomly. Let's say, imagine the system's trying to get its way through a maze. It'll start out randomly, just walking around, right? And if after a while it doesn't get through the maze, it's going to say, okay, well, didn't do this correctly, right? And so if it finds a path that seems to be promising, that'll be reinforced, and so on. And typically, a lot of systems will use all three of these. But here's, and they also require large amounts of data. But here's the important difference, I think, with machine learning. Whereas over here we have a program, we have input, and we have an output. In here we have the input and the output. So for example, if we're trying to get a system to identify cats versus dogs, we know what the input is, here's the image. And we know what the output is, dog, let's just say, like, it's dog. And what we want to get out is a program that is going to be able to predict for the next image, is it a dog or a cat? So it kind of inverts the kind of classical system. If the output is the program, it is the algorithm. We typically, by the way, we call that program that comes out of a machine learning algorithm, it is itself an algorithm. It is itself a program, okay? These are essentially meta algorithms. The output we call a model. Because it's supposed to model something. It's supposed to represent something. So that, for example, it's supposed to represent whatever the relationship is between dogs and these images, right? Okay, two kind of examples of this. Search planning, like I mentioned, Google Maps, Google PageRank algorithm, which is the algorithm you use every time you search something for Google. That is a classic search algorithm. Gameplay, if you ever played chess online, you are working with a search algorithm. It is searching all the possible options in chess. using some very interesting kinds of rules to kind of weed down the number of moves you can consider, because there are more positions in chess than there are atoms in the known universe. So a program, this is a big bottleneck. The program can't proceed by considering all the possible moves. Instead, it has to have certain what we call heuristics, rules of thumb, that tell it this is a bad way to go, right? This is a dead end. Let's just focus on this narrower set of possibilities. Medical diagnosis, like I mentioned, expert systems. These are used quite often in hospitals to help doctors diagnose. Just here are some images, like where you have a search tree. Each one of these like nodes here will represent, say, a position in a maze. And so the algorithm will search through this tree to figure out, oh, what the, I'm just messing this up. Oh, we're going to do that. In the case of supervised learning, a classic example is what's called linear regression. If you've ever worked with Excel, you probably will know something like this. I have a bunch of data points. Maybe it's, let's say, you know, how many,
At least we know you're not an AI bot.
oh, yeah, well, actually, I mean, maybe. In any case, the idea is you have data and you fit a formula, an equation that best matches that data, and it'll allow you to predict future data points. This is just, if you've ever used Excel and you've done a linear regression, congratulations, you're doing machine learning. Right? That is machine learning right there. Applications of this include things like credit scoring. Right? We want to predict how likely is this person to repay a loan based on their previous credit history. Well, the credit history is those data points, and we run a regression to try to predict the next data point, how likely are they to be well qualified for a loan. Parole boards, we're going to talk about that in a moment, about how algorithms are used to predict recidivism rates in prisons. All right, well, the big thing you've probably heard about these are artificial neural nets, generative AI. Can't go into details, obviously, but here's this little image, right? Dogs and cats. These are little neurons. They're basically themselves just algorithms. They take some inputs, usually coming from other neurons or from the data that we give in, which in this case would be just the pixels, right, on the image. All those pixels can be represented as a number, right? It's important to remember, when you see a computer program, image recognition, it's converting all of those pixel values into a number. And then it's just running on that number. What that number does is it influences the behavior of these neurons by giving it certain inputs, certain weights, and then those cause the neurons to fire to the next level, and so on and so forth, until you get down to the last layer, and that's going to have something like, okay, if the value is above a 5, it's a cat. If it's below a 5, it's a dog, something like that. And then the real thing that unlocked this artificial neural net program, or architecture, we should say, that was developed in the 40s, was this algorithm called backpropagation, which allowed these systems to learn. They figured out a way to get the weights that each neuron assigns to all the neurons in the other layer, figured out a way to update those in order to minimize the error on the output. This was a big breakthrough. It happened in the 80s, but it really didn't pick up steam until the 2000s. And it was discovered, wow, we can get these systems to perform incredibly well on a number of tasks that were historically very difficult, including things like image recognition. This was not something that GoFi could do well at all. Artificial neural nets seem to do very well at this. It's part of what's called a connectionist program. This was a different way of thinking about cognition. The idea was that cognition is not necessarily symbolic. So if you think about the GoFi, it's based on a view of thinking as linguistic. The idea is that when we have thoughts, they are represented in a linguistic fashion. And connectionism doesn't think that. Instead, it's kind of pattern-based, and it's based on the kinds of activations that occur between our neurons. And so you have this very different way of thinking about thinking that underrode this development. The big thing you're hearing about is generative AI. So these are deep learning models. So deep learning just refers to artificial neural nets, right? Deep learning are these machine learning programs that are based on artificial neural nets. They can produce high quality images and text. This is ChatGPT. You've heard of this. ChatGPT, right? DALL-E, all the image generators. These were models that were trained on massive amounts of data, arguably most of the internet for ChatGPT. And it was unsupervised. It basically, researchers said, find the patterns. Find the patterns. In the case of GPT, it was predict the next word. So imagine feeding this machine just terabytes, millions and millions and millions of gigabytes, okay? Feeding that these images or text and trying to get it to predict the next word, right? You already have what the next word is. So you can see whether it's done well or incorrectly. And then we give it to a new task, and it's able to generate, predict the next word. It can actually write the next word. These are a version of what are called foundation models, and this is the big revolution that's happening. You have these models, like ChatGPT, that are trained on more data than you could possibly imagine. And then they can be used for specialized tasks by fine-tuning them. For example, ChatGPT can be hooked up to a robot, and it's showing to be amazingly effective at navigating an environment. Like, what, ChatGPT is a language model. It predicts the next word. Well, it turns out, once these models have been developed, you can fine-tune them on a new set of data. For example, the arrangement of objects in a room. And it can perform extremely well. And here's the thing that is admittedly scary. Even the people who do the research here don't know why. This is the big thing about deep learning. We don't know why these models perform as well as they do. Unlike GoFi, where we can get in there and see everything's nice and symbolic and logic-based, deep learning is not. Typically, researchers working in the field will not know why one model does better than another, except to say, well, it's got more neurons, or, oh, we gave it more data. And this is where one of the big challenges comes in, transparency. And we'll talk about that in a moment. Let's talk about it now. Big issue is accountability and transparency. Lots of models are inaccessible because of intellectual property. That's a big, important barrier to transparency. But even when they are publicly available, the researchers themselves, experts, don't know why the model does what it does. And this is a deep ethical challenge because we live in a time when we have a right to reasons. This is a fundamental, I think, part of modernity is that we have a right to reasons. When decisions are made that affect us, we have a right to request for reasons, for explanation. We may not agree with it, but we deserve the reasons. When you go to a judge and you're sentenced, the judge has to provide reasons for that decision, even if you disagree with it. And there is no way to do that with these models. You cannot ask the model, why did you do this? Because even the people studying it don't know why. And that is arguably one of the biggest challenges facing this. And that's why the program of XAI, explainable AI, is really big right now. How can we augment these models in a way that makes them explainable, that makes them more transparent? It's a big challenge. Trust, right? A lot of these models are unreliable, or they've been used in new areas that are unreliable. The evidence can be inconclusive, and there's just these massive data sets with all kinds of biases riddled throughout. And a lot of times, for example, the people who train ChatGPT, they don't even know all the data they fed it. We're talking about most of the internet. Imagine going through, most of the internet. And none of it was labeled, none of it was curated. That all happened on the back end to try to kind of clean up the offensive language and the derogatory comments that were coming out of this system. These were all cleaned up on the back end. Safety, obviously, this is a huge issue. These models give lots of power to malicious actors. We know that, for example, deep fakes, if you've ever heard of deep fakes, these are AI-generated images or typically video that are completely fabricated. So you may see ones like Obama giving, some speech that he never gave. That's really, really scary, admittedly, right? And there's a lot of work being done to try to mitigate that possibility that you might be, inundated with images and videos that are not authentic. Given the fact that videos now play forms some of the best evidence you ever get in a courtroom, right? the idea that that could be completely fabricated is pretty scary. And so we have a lot of work to do on that. Another issue that often doesn't get attention is the threat to autonomy. So we tend to think that when we decide to buy a product or go to a movie or something like that, we're making the choice autonomously. Nobody told us to do it, nobody forced us to do it. But what happens with AI-generated personalization, so this is like the recommendation systems on Netflix or on Google, right, that tell you, here, you should try this out. Now, a lot of times they're very helpful, honestly, but there is a potential threat to autonomy because what happens is you have your choice structured in a way that nudges you in a certain direction. This was a big term that came out of the Chicago School of Economics, nudging. This idea that planners, that is, and politicians and policymakers could actually use our implicit biases to get us to make better choices. For example, taking the healthy cereal, let's say, and put it at eye level, or the fruit goes at eye level. We have a tendency to choose things, not always, at eye level rather than below. And so that kind of nudge can happen in AI systems. You just looked at this website, we're going to feed you some commercials. And so there's a real question about whether or not our autonomy, our ability to make free choices is compromised by that, or even if it's not, or even if it is, I should say, if we lose a little bit of autonomy, it would be at least nice to know that our choices still align with our values. Okay, I didn't make that one freely, I was kind of nudged into it, but at least it aligns with my values. That's not clear. It's not clear that those choices will still align with your values. And the last is fairness. Algorithmic bias, data drawn from discriminatory practices, and most importantly, what are called proxies for protected attributes. Protected attributes are things like race, gender, sex, sexual orientation, ability, and so on. Lots of machine learning algorithms are trained on massive data sets that have no information about race, and yet they end up producing often discriminatory and racist outcomes. We're going to talk about that right now. The story of Compass. You may have heard about this. This was a big story about 5 years ago. Compass is the Correctional Offender Management Profiling for Alternative Sanctions algorithm. It's used to predict recidivism. That is, how likely somebody who has been incarcerated is likely to reoffend, specifically be rearrested. That is actually an important qualification. We're not actually talking about whether they commit a crime again, it's whether they are arrested again. Nonetheless, the term recidivism is what's used for that. It's a proprietary tool. That means we don't have access to the algorithm. It's protected by intellectual property. It assigns risk scores to individuals, basically how likely are they to reoffend. And it does this based on a questionnaire that asks about prior arrests, criminal behavior, among friends and family, employment, housing, substance abuse, and personality traits. So there's a kind of personality questionnaire that goes along with it. Importantly, it doesn't ask anything about race. It is race blind. And it's used in jurisdictions across the United States to make decisions about pretrial release, sentencing, and parole. I'll mostly be thinking about pretrial release. So this is where an individual is brought in for arraignment, and the judge has to decide whether or not to grant bail or whether to detain them pretrial. Now, notice that's a really, the stakes there are very high, because both on the side of falsely imprisoning somebody for a crime they may not have committed, we know that that's terrible, but also potentially letting loose somebody that could, cause harm to the community. So it is a high stakes and difficult decision. And judges actually requested this. They wanted something more objective, you might say. That's rather questionable whether it's more objective, but let's talk about the results. So ProPublica, which is an amazing investigative journalism outlet, they argued that Compass, after looking at a lot of the decisions that were made on the basis of Compass, that it was biased against blacks, since it yielded higher rates of false positives. So in other words, people who were not going to reoffend were more likely to be labeled high risk if they were black. Let me say that again. you've got somebody who is not likely to reoffend, and yet they're labeled high risk. That happens much more if the individual is black, if the defendant is black. And conversely, there was a higher rate of false negatives among whites. In other words, if you were a white person and you were going to reoffend, you were more likely to be labeled low risk if you're white than a black person. That seems unfair. Right? There's essentially an inequality of risk. If you're black, you have a much higher risk of being falsely imprisoned despite not reoffending. If you're white, you have a much lower risk of being falsely imprisoned. In fact, you're more likely to not be in pretrial detention even though you will reoffend. So that unequal distribution of risk seems unfair. So, yeah, okay. Well, North Point, which was a company that developed Compass, they responded. They said, well, there are these discrepancies among false positives and false negatives. The percentage of blacks assigned a risk score was the same as the percentage of whites assigned that risk score, meaning that the algorithm was what we call well calibrated. But basically, this is the point. If a black defendant and a white defendant are equally likely to reoffend, Compass will give them roughly the same score. So if somebody has, let's just say, I'm putting numbers on this, 80% chance of recidivating, it won't matter if they're white or black. Which is also something that we think is fair. Imagine if it did. Imagine if the black individual was much more likely than the white individual to have a score that misrepresented their recidivism, maybe in a bad way, predicting that they would recidivate much more than they actually would. Imagine there was that difference between whites and blacks. So essentially the scores meant different things whether you were white or black. That would be unfair. So the fact that the algorithm does this is a point in its favor. This is an important part of fairness. Imagine I had two sections in my class, and one section I routinely would give them 80s when they deserved 90s, and the other would get 90s when they deserved 90s. You might think, well, there's something unfair here. Like, you're systematically biased against this section. That's what it would be like if this weren't the case. Here's the rub. First of all, we've got two measures of fairness. One is what ProPublica says. This is error rate parity. It says basically the false positive rate and the false negative rate, they should be the same across whites and blacks. And then the calibration. Scores should be equally accurate. In other words, the score shouldn't be like more inaccurate when it comes to blacks or whites. They should be the same regardless of race. Here's a way to think about this. So here we have black defendants, low scores. The red shows the people that do recidivate, that is, they do reoffend. Here we have those that got high scores. Again, the red shows those that recidivated. The green shows those that did not. And same over here for whites. So now look at this. The low score in blacks, look at how many, right, don't reoffend. But look over here at the high score in blacks. We see a good proportion, right? They do not reoffend, and yet they were labeled high score. That's the false positive rate. That's Compass saying these people are going to reoffend when they don't. Look at the white score. Oh my gosh. Look at the low score. Look at how big, right, the low score is. And look over here at the high score. Look how much smaller that portion of people who were said to be reoffend, the people with high score, very few reoffended, or a small proportion. Now here's what's really interesting. When I said about calibration, the idea the scores mean the same thing, you can see the proportions are actually the same. In other words, if you look at that red there, right, and look at the red there, you can see, oops, the proportion is the same, right? If we were to actually just stretch this out, you would get something like that. That's well calibration. That means the scores mean the same thing regardless of race. The false positive and false negatives comes in here. Look at the proportion of this yellow to this yellow. It's much different from that blue to that blue. That's the false positives and false negatives. In other words, here you have many more people that are not going to reoffend getting labeled high risk versus this. Over here, very few. And look at all the people here, right, compared to that. That's the false negative, false positive rate difference. Here's the rub. when the base rates of a value are different. So base rates here means how likely is a black defendant, if I just took them at random, how likely are they to be rearrested? That's higher than for whites. This is a fact. Blacks are rearrested at higher rates than whites. Probably not a shock, right? Blacks are rearrested at higher rates than whites. That's the base rate of rearrest. When that's different, you can't get both values. You cannot have equal false positives, false negatives, and calibration. You have to give one up. This was the big result. Here are two seemingly perfectly plausible metrics of fairness. You cannot have both. Well, there is a way to get both. You could decide that blacks and whites, the scores mean different things for them. So say, a judge could say, well, you got a .8, but you're black, and I know that there's a different false positive rate, so I'm not going to put you in pretrial detention. Oh, you're white, you got a .6, I will put you in pretrial detention. So in other words, the only way to correct it is to be explicitly racist, or at least to consider race explicitly. And that's what some people think that should be done. This is a hard, hard choice to be made. It's not clear that we have to make the choice always, but in most realistic situations, we're going to have to trade this off. That to me is one of the biggest things that's come out of this, that there is systematic unfairness in these systems, and they're not easily solved. Some long-term considerations, climate change, right? So we know that these deep learning models require a lot of energy, so there's a lot of concerns about the energy consumption, and of course the carbon footprint. Automation, probably one of the biggest concerns, right? Automation, displacement of workers. Something to remind you, some of you may remember when accountants were physical people and had large teams requiring the building of spreadsheets, which was a physical object back in the day. Those jobs are gone. And they disappeared over the course of 20 years, from the 80s through the 90s, because of Excel. Right? Most of the accounting industry just disappeared. And yet, right, there are thin fall and people found other jobs. So there is some sense that there may be ways to transition effectively with the introduction of automation. At the same time, of course, right, folks in the creative sector are very worried about AI. I have a brother-in-law who does design for beer labels, and he just got his first rejection, essentially. His employer said, no, we don't need you, we're using AI. So there's legitimate concerns here, but it's not obvious that this can't be dealt with. A huge issue is the moral status. If we actually get human level intelligence, do they deserve rights? What about relationships between AI and humans? And then, of course, there's some concerns about superintelligence. There's this concern that if you have an artificially general intelligence system and it gets to design its own artificial intelligence system, you'll have what's called an intelligence explosion, where you have hyperbolic growth in intelligence, so that we have systems at a certain point that consider us the way we consider ants. Not as something worth even spending some time about, unless they're an inconvenience. That's the concern. How serious is that? It's not an immediate one, I will tell you that. Definitely not an immediate concern. And I think there's a lot of reasons not to worry about that, though it is something that should be on the radar. All right, guys, I'm sorry I took way more longer than I wanted to, but that's going to be it.
Who's got a question?
I know, I just
Who knows
realized.
how to
I got
write
one.
questions? There you go, Brian.